Hey guys, welcome back to Quick Code. Today we're doing another Brainstellar Quant puzzle. This one is called Distance from North Pole. It's a hard problem. You guys can pause and go over the problem once. So, first of all, to answer the further thinking question, the answer is yes. Considering the two cases, the first case of choosing two random points, and the other case having one point fixed and the other point chosen at random. Now, for both of these cases, if we are to calculate the expected distance between the 2 points, the question is the exact same. This value and this value is completely identical. Because, well, with respect to calculating the expected distance between the 2 points, just picking two random points or having one of them fixed and then choosing another random point, it's both of them have the exact same solution. So coming to the problem now. So imagine we have a sphere, right? And this is the North Pole at the top. And we have to imagine this as a perfect sphere of radius 1. Now what we've been asked is that we are going to pick a point at random on the surface of the sphere, and what we have to calculate is the expected distance between the North Pole and the random point that we choose, right? So basically this. Now, to start off with a few hints for this problem, but since we're asked the expected value of the distance between the 2 points, let's just write the formula for the expected value, which is basically going to be the summation over each point possible on the surface of the sphere. So yeah, the summation of all the cases, and where the probability is the probability of that point being the randomly chosen point into the distance between the point. So let's just call the point as P. So into the distance between P and the North Pole, right? So this is in general what we have to calculate, right? So this is the value that we have to calculate for each case, and each case is defined by a point on the Earth's surface. We first of all calculate the probability of that point being chosen into the distance between the point and North Pole, and we sum over all of those cases, right? That just means each and every possible point on the surface. But this has a problem because, first of all, the probability of a single point is always going to be zero, and it's pretty common in many calculus or physics problems that when we've been given a 3D setup, usually the element we choose is of 2D, right? Or it's always one dimension less, right? So try to think of some two-dimensional elements that are very common when it comes to calculus or physics problems. So there's one very common element that is chosen when we're talking about a sphere, and that is a ring, right? So basically imagine a small ring around the Earth's surface. Now, if we take a ring as depicted over here in the figure, which is basically cutting the sphere horizontally, right? Now, there's a big benefit of taking a ring like this, because if you notice, then each and every point on this ring is going to be equidistant from the North Pole, right? So this is going to help us with our calculations. So now the value that we have to calculate, the expected distance, can be simplified to as something like this, right? And notice that all we need is distance between any point on the ring and the North Pole, because all of the points on the ring are equidistant from the North Pole. So, and another thing we have to notice is, because since we're taking elements of this continuous 3D shape, it's actually going to be an infinite number of rings, and for that case, we, instead of using summations, we use integrals, right? So now let's come to the proper solution. So first of all, let me draw the sphere, and let's do the North Pole. And what I'm gonna do is, let's take an example element, so an example ring, and the way we define each ring is through an angle theta, which is going to be depicted as over here. So each ring or each element is going to be defined by the angle theta, right? So for each unique value of theta will give us a unique ring. Now if we notice that every point on this ring is going to be equidistant from the North Pole, and this distance is going to be 2r sine theta by 2. This can be proven pretty easily. It's a common result, so that's why I'm just writing it directly. But, well, if you want a quick explanation, so if we consider this value is theta, this as r and this as r, and we want to calculate the value of this line over here, what we do is we draw a perpendicular, and this is also perpendicular bisector, because this r and this r is the same. These angles become theta by 2, and so if we look at this triangle over here, right, this is r and this angle over here is theta by 2. So this half this length over here becomes r sine theta by 2. And if we just double it, we get the entire length, right? Which gives us 2r sine theta by 2. Yeah, so, okay, so for any ring which is defined by the angle theta, the distance factor we already understand now, which is it's going to be 2r sine theta by 2. Now, what the other component we need is the probability of this ring being chosen. For that, we're going to look at the area of the ring divided by the total surface area of the sphere. Well, we already know the value for the denominator. It's going to be 4 pi r square. But now let's look at the area of the ring. So let me just draw this figure again. And now imagine a d theta. And this is our ring. By symmetry, this angle here is also going to be theta. Now these two lines are r, right? Because they're the radius. Now to understand the surface area or the area of this ring, imagine it as a rectangle or a ribbon, right, which is wrapped around the surface of the earth. Well, actually it's going to be something like this, but in calculus we can basically approach this as something like this. And all we need for this ribbon is the width and the length of this ribbon or this rectangular strip, right? So first of all, let's talk about the length. So for the length, we know that it was basically a ribbon wrapped around the surface of the earth. So it was actually this small circle over here with a radius as this value, right? Try to pause and imagine. It's what this length is actually it's the circumference of a circle having the radius as this value depicted over here. And how do we calculate this value? Well, let me just draw this triangle over here. So because this value is theta, this value is going to be pi minus theta. So we have pi minus theta over here, and this value is r, right? And we drew a perpendicular bisector, so this is going to be 90 degrees. So this value over here comes out to be r sine theta. And since we want the entire length, and we know that this is just the effective radius of the circle, this radius is going to multiply by 2 pi to get the entire length of, or basically the perimeter of the rectangular strip. Now all that's left is the width. Well, if you look at this arc length over here, since I said that we can approximate this arc length to be a vertical straight line, we can just calculate the value of the arc length, which is going to be, if you look at this small portion over here, it's pretty obvious to see it is rd theta. So the W value comes out to be rd theta. So overall, calculating the area of the ring comes out to be width into length, which is going to be 2 pi r sine theta into rd theta. And to calculate the entire probability is going to be dividing this by 4 pi r square. Now all we have to do is to calculate the expected distance, and we plug in the values we just calculated. Now it's also important to understand that to cover up each and every possible ring on the surface of the earth, we are going to let theta vary from 0 to pi, right? Because there's going to be a ring of 0 or very close to 0 as these rings. Then there's going to be rings over here for theta values like these. And as we go along, this ring is going to be theta is equal to pi by 2. And as theta approaches these values over here, we're going to have smaller rings. So you can see that theta is going all the way from 0 all the way to pi. So we're going to integrate over 0 to pi. First of all, we're going to write the distance part, which was 2r sine theta by 2. So this is the distance part. And then we multiply this by the probability part, which was this value over here. Right? So just plug in this value. So this in itself is a pretty simple integral. Basically, you'll get a term something similar to sine A sine B. For that, you have to use the trigonometry formula of cos of A minus B minus cos of A plus B. And it boils down pretty quick. And solving this integral, you get the value of 4 by 3, which is the answer to this problem. I hope you guys understood this solution, and thanks for watching.